All right, folks, happy Thursday. It is revision time, section 3.5 exit ticket. And I just wrote back feedback to every bunch of people, but some people need to, take a look at this, make some revisions, find the problems that maybe I gave you feedback on and you need to revise and then re-kick back in, right? So I can give you guys the credit for this here. It's the section 535 exit ticket. Revision is super important, right? Because most classes you'll take in the future, you're not going to get things right away, right? So that's big here. A lot of times, maybe in middle school, you feel like you got it right away. You got to learn from revisions and push yourselves because this stuff is beautiful, right? It is really, really nice. You just got to push yourself and learn from revisions and get there. The better you can get it now, the more beautiful it's going to be later. Okay, so we're going to look at one person's exit ticket. They did pretty well in the first several problems in here. I think they rented some mistake here on part 6. But just real quick here, in case you need to revise yours here are the answers to part 1 here. 5 trial congruency shortcuts. What's your postulates? What's your theorems? So the ones we've been using all along, right, up until section 3.5, are postulates, SAS, ASA, and SSS. That was the one from the video lecture where we just noticed this, right? If we put 3 sides together, right? Remember that I did that with the constructions, remember the little compass thing I did in the video? If I put 3 sides together to form a triangle, I can only find one kind of triangle set up. So if I have 3 side lengths that are all the same in one triangle, versus 3 side lengths that are all the same in another triangle, they would correspond with one another, they'd be congruent. And that's just purely through observation, something that we see. We can't prove it. We don't have a foundation. We don't have a basis for saying that that's definitely going to be true every single time because we can prove it based on other theorems and postulates. It was purely based off of observation. That's why it's a postulate. And the same thing could be said for the SAS and ASA. That was the same thing too, where we did that more on the PowerPoint, right? With stuff moving around. If I have 2 sides that are congruent and an included angle that are congruent, I can only form one type of triangle, right? Only form one type of triangle, okay? So what you did in section 3.5 is you learned some new reasons, right? That was the important thing, learn some new reasons. But AAS or SAA, you can call it either one, right? Because the idea is that it's a non-included side you would know is congruent one triangle to another triangle here. If you have an AAS correspondence, you can say the triangles are congruent, and that's by a theorem. That's by a theorem. So AAS is a theorem, and you should probably remember that in AAS is a theorem because we proved it yesterday. We did it in class. We did it in a lesson video, but we prove AAS if we're given an AAS correspondence between 2 different triangles. Remember, we can prove it that 2 triangles are congruent through ASA, right? ASA, because the AA means you have a pair of angles congruent between 2 different triangles. And when you have a pair of angles, 2 angles in one triangle, congruent 2 angles in another triangle, then the third angles are also congruent. Remember, third angles are also congruent. So you can get that third angle congruent, and then you have an AASA correspondence. Think about it that way, AASA, and then you can use ASA to prove the triangles congruent. So that's why we know we can prove that AAS is actually a theorem based upon the ASA postulate. Okay, so anyway, I know it's confusing. They're so similar, but you can use postulates, right? If we accept them, if we just accept them that they got to be true, we can use them to prove other facts that we'll call theorems, right? That can't be argued with as long as our postulates came from the true place here. Okay, same thing with HL. HL is the other theorem, not SSA, not AAS. Remember, you're never using AAS in this course. Future courses, you might use them because they're true in certain scenarios. They're true for right triangles. But SSA is true for right triangles. You use HL. Use HL in the proof, and HL is the theorem that was in last section, okay? The hypotenuse leg theorem, okay? Because if I know 2 sides of a right triangle are congruent to 2 sides of another right triangle, I want to know that they're congruent. It could be through SAS. SAS, if I know both legs in both triangles are congruent. Okay, that'll come up in your homework today. But if I know a hypotenuse and a leg are congruent, I also have the right angle too. But whatever, I have a right triangle here, right triangle there. Hypotenuse and a leg congruent to one triangle to another triangle. I know that they're congruent, okay? And that's a proof. That was that 14-step proof, which you see a little bit later in this exit ticket here. All right, part 2 here. Some people, again, fast forward if you got this. I'm going to tell you which problems to look at here. But here are some good, this is a good answer here for HL. So remember, HL theorem is kind of like the SSA, ASS for right triangles, okay? So you still got to say 3 things in a proof because the way that the HL theorem is written, it starts with if a hypotenuse and a leg are congruent to a corresponding hypotenuse and a leg of another right triangle, then the 2 triangles are congruent, okay? So obviously you need to say the hypotenuses are congruent, you need to say that a leg is congruent, and you just say that the sides are congruent. Right? Sides are congruent. You don't actually say that they're a hypotenuse. You don't actually identify that. But in the proof itself, you should also say that they are right triangles. You should also say they're right triangles. So these answers are totally correct right here. And maybe we should actually look back to figure out why this is important, why this comes up here, because the idea is, remember, to use a theorem in a proof, you have to fulfill everything that's after the if statement here, okay, after the if statement here. So check this out here. If the hypotenuse and a leg of one right triangle are congruent to the corresponding parts of another right triangle, then the triangles are congruent, okay? So you need to say a hypotenuse congruent to another hypotenuse, or like a side and congruent to another side. That would fit the definition of a hypotenuse. You don't need to say it's a hypotenuse in proof. You need to say another side congruent to another side, and that has to be one of the legs. But then it also says of one right triangle, okay? So in the proof, you got to tell me it's a right triangle. You got to tell the reader it's a right triangle. That way, you can justify using the HL theorem. So justify using the HL theorem, you got to say everything that's in the if here. So in order to use this theorem, remember, you're using this theorem to prove that triangles are congruent, okay? So how do I know that two triangles are congruent? One, they are right triangles, okay? So you say that, right, as one of the things you say before using HL. You establish that they're right triangles, then you establish that a hypotenuse is congruent to the other hypotenuse. And then finally, you establish that one leg is congruent to another leg, okay? Do you need to do it in that order? No, you don't need to do it in that order, but just even though HL, so the reason why I make a point of this here is that HL only has two letters in it, okay? So a lot of people think, hey, if I can prove that AB is congruent to DE, then I can, and I prove that BC is congruent to EF, then hey, I can just use HL and say that these two triangles are congruent. Well, no. Have you told me yet that they're right triangles? Have you told the reader that? Have you told the person analyzing your work that here? Okay, so this answer is A-okay, good to go. Okay, because you gotta establish this for right triangles only. Then you just gotta tell me those two sides, right? The longest side and then one of the legs here, congruent to the triangle here. Okie dokie, yes, question mark there. This was in a video a few days ago. I'm gonna move on, but there's your answer. There's your answer. Don't be one of those. Don't be one of those. Don't be a donkey. A lot of people are writing a donkey here. Anyways, hypotenuse, legs. There we go. There we go. So remember, only like one or two people got this one wrong here, but hypotenuse is the longest side. It's opposite. Right, opposite the right angle is the as a hypotenuse, and then adjacent to the right angle here are the legs. Okay, there are two legs here. Sure, there's a shorter leg. Sure, there's a longer leg in this particular diagram, but they're both called legs. Okay, because legs will come up important in the way it relates to the hypotenuse next semester with the Pythagorean theorem. All right, there we go. Everybody said yes here. Nobody was like, I'm sad. I didn't copy this all down. Anyways. Fun proof, 14-step proof there in the book for the HL theorem. We'll keep moving on here. Part 6. Okay, don't look at these answers here because they had a question mark here. That one they didn't quite get right. They actually didn't quite get the SAS one right as well, I believe. Yeah, AEB. So these two triangles are not overlapping. So I'll probably write that feedback to that person here, or I'll just address it in this video. So what we're going to do is we're going to move this to, or I'm actually going to click out of this here. And I'm going to open it up as if I were a student. We can talk about these ones together. Okay, so each of these diagrams here, these are some of the classroom exercises from this section. Figure you get them out of the way now rather than during your problem set today. It says, for each diagram, name a pair of overlapping congruent triangles. Tell whether the triangles are congruent by SSS, SAS, ASA, AAS, or the HL methods. So those are your 5 methods. Remember, SSS, SAS, ASA, postulates, AES, HL, theorems. Does that matter in this problem? No. Do I need to remind you? Maybe, because a few people got that wrong on the very, very first slide here. Okay, so check this one out here. You know what that person just said was that AEB would be congruent to DEC. That's not correct because the actual triangles need to actually overlap here, and they're not actually overlapping, right? In order to overlap, you need to have a side in common, or you need to have an angle in common. Right? You have to use the reflexive property to actually to fit the definition of overlapping, right? Even though we haven't fully defined that, we've kind of talked about that so far. So what jumps out to me in terms of overlapping aren't these two triangles right here. They got to share a side. So boom, boom, boom. There we go. That triangle and boom, this triangle here, okay? There we go. So those two triangles right there. So this may have been a little bit easier if you had taken this actually and marked up the diagram. So if you had marked up that AB congruent to DC, okay, and then you marked up AC congruent to DB, and that's a little messy, right? Because we have to go across here. So I'm going to tick mark this, and I'm going to tick mark this. All right, getting messy here. So we have that side congruent to that side congruent to that side, and Why did I mark it up like this? What's overlapping here? What's overlapping here? Yeah, we have BC. Okay, we have BC right here. BC overlaps upon itself. So down there, okay, right? BC equals BC by the reflexive property. Okay, that means, right, we found an overlapping triangle, right? It shares one of their corresponding parts. Has the same thing, right? It's the same shape. It's that segment, and we're good to go. Okay, so now we need to summarize. We need to write down kind of what our answer is here. Triangle ABC. We got to do it in a way where the correspondence is accurate here. So AB segment AB corresponds to DC. Triangle DC and then B, right? Because BC here corresponds to CB. Yeah, we're good to go. And BD corresponds to CA, yeah, I'll buy that. I'll buy that. By reason of, well, did we prove angles congruent? No, we proved 3 pairs of sides are congruent because we had 2 pairs of sides, a side here, a side here. Oops, we can do it in a different color because we have these colors at our disposal. So we have a side here, we have another side here, and finally we have another side here, right? So that's how you prove it, SSS, okay? By reason of SSS in this particular problem here. All right, moving onward here. So let's get this one here. This was probably the trickiest one for people. Few people got this one wrong. Most people got that one right, but a decent amount of people got this one wrong. This was tricky. And this also too is like kind of a brain buster for me, but more people are getting that one right, I think, than number 12 here, okay? Number 12 here, you got angle ABC is congruent to angles ACB. First step, mark up your diagram. I didn't do that up here because I just figured I'd show you the triangles. We talk about overlapping triangles is in this instance here. Down here, now that you know what overlapping triangles are, we'll worry about that later. So first step, we'll mark down our givens because they're giving this to us for a reason, right? 99% of the time they give you a premise. It's, and this is a premise right here because it's a given next to us here. It's a given fact. 99% of the time they give that to you, you're going to use it in order to get to what you need to achieve, which is proving that 2 triangles are congruent to one another. So here we have angle ABC, and that's right here, congruent to angle ACB. And so what should jump out to your brain now, right? What should jump out to your brain? We're given 2 angles of a triangle are congruent to one another. So therefore, what can we conclude? Well, when you're given two angles of a triangle are congruent, or somehow you prove 2 angles of a triangle are congruent, you should immediately think that, what about the sides? 2 sides would have to be congruent here. So again, the ITT, isosceles triangle theorem, and the converse ITT, and its converse, CITT, are 2 of the most used theorems in the book here because they're going to help get us from those congruent angles to congruent sides. So this is the converse ITT. So I'm going to go ahead and mark this up. Those 2 sides would be congruent. AC congruent to BC, to BA, okay? So that's good. That helps us. I know that about this large triangle, but remember, I'm trying to prove congruent triangles. So now I got to think, well, these angles, I got these angles right here. I got these sides. Maybe how can these sides help me determine overlapping triangles here? Okay, so let's see here. This side, we have this angle. Well, that angle, not necessarily going to be in the same triangle necessarily for us to prove. A lot of people are drawing like a perpendicular here and finding this. Oh, okay. Actually, you know what? I see some people who may have gotten this right that I didn't see so far. Interesting. Okay, I won't actually say that out loud, so it's pretty neat here, but I'll keep an eye out for that when I'm looking at your exit tickets. Okay, anyways, the overlapping triangles that I see here now jumping out to me is, remember, your overlapping triangles can overlap in terms of a side that they share in common, but they could also share an angle. Okay, so notice here, this is AB, it's congruent to AC. We're not going to worry about that now, but I'm going to highlight a triangle that I'm going to make a case for that triangle being congruent to this triangle. Okay, what's overlapping in those triangles? The purple triangle and the red triangle, what's overlapping? That's right. Do any sides overlap? No, sides don't overlap. Angle overlaps here. Angle A is congruent to itself. So here we have an overlapping triangle because it shares an angle, right, with one of the triangles. Angle A is congruent to angle A, and that again is through reflexive. I'm going to switch to my stylus here so I can write this a little bit faster. Reflexive. Okay, that's reflexive right there. So I have an angle in common. I have a side in common. And what else do I have in common? My diagram is getting really, really messy here. So perhaps you're having trouble seeing it, in which case we can meet and talk about it here. But I also have an angle here. Look, I have these two right angles right here. So the purple triangle, I have an AS correspondence. The red triangle, I have an AAS correspondence, right? AAS correspondence, okay? So I'm going to sort of summarize it. You might have trouble seeing. You might have to look really, really closely here. But I'm going to summarize this and put this one down. There's a reason why people have the hardest problem with this one. Yeah, it's hard to see here. It's like really getting down in the diagram, really breaking it down here. It can be difficult. So anyways, triangle ABD is congruent to triangle ACE by reason of AAS. Okay, reason of AAS. All right, so that's maybe all I'm going to say about that. Perhaps look at it, rewind, rewatch it, see if you can figure that out. There's your answer there. I'm actually going to show you another way, though. I'm going to show you another way you could have gotten this one because there's actually more than one pair. It's pretty neat. There's more than one pair of overlapping congruent triangles in this here. So we talked about that one here. There's other overlapping triangles. You guys actually see it here. I'm actually going to mark it up. Perhaps you saw this one faster than I did here. So remember, we're given this as our opening premise. So angle ABC congruent to angle ACB. And these are actually congruent angles in two different triangles that are going to prove congruent to one another. Which ones? That's right. BEC and DCB. DCB. Those ones down there. We're going to prove it. What do they share in common? Oh, they share BC, segment BC. Okay, so let's go ahead and maybe mark that up here. So we have the angles marked up here. Maybe I should do that in different colors so we can really notice what's happening in both of these triangles here. So this is angle DCB right here. And that'll be this triangle I'll talk about here. I'll use purple for this one. Okay, so this side right here down below is congruent to itself. Okay, BC is going to correspond with CB here. And BC equals CB by reflexive. So it overlaps. Okay, if we're using the reflexive property, that means we have an overlapping triangle in some case here. All right, overlapping here. So we have an angle, we have a side. What else do we have? Well, these are marked up here. Those are right angles up here. Is that good? Well, the definition of perpendicular is if we're perpendicular if we make one right angle with two intersecting lines, we make four right angles, right? They're all right angles here. So this is a right angle here. And this is a right angle here. So here we have right angle. It's not HL because we only have one side here. A lot of people said HL in this problem here because we know this hypotenuse is congruent to itself here. But do we know a leg is congruent to another leg, right? A corresponding leg is congruent to another corresponding leg in this diagram here. Do we know that yet? No, we just know that this is a right triangle, and right triangles have angles that measure 90 degrees. So those two angles are congruent to one another, right? They're congruent to one another. And this diagram is really messy. That's why you got to be listening to me right now, I guess. So here we have an AAS correspondence here. Okay, so I can actually write that down. You don't have to do this. You just needed to get one of these correct to really nail this problem here. But I'll write them down too in case you noticed it and you're just like, wait a minute, Mr. Ford, can I do it this way? Yes, you absolutely can. So triangle EBC is congruent to triangle DCB by reason of AAS. Okay, and we're good to go there. I'm wondering this actually too. If any of you guys did something awesome, went above and beyond here, and made this argument here, because actually I've been correcting people so far who have said HL as a reason here. We're not going to have HL, I believe, here. So unless potentially this works out, because I've actually been seeing this drawing, I haven't really thought about it much. But if I knew that that angle is congruent to that angle, and I do because that's a given premise of the problem, right? It's right here. Okay, I can make the conclusion that this is an isosceles triangle. Okay, this is an isosceles triangle. What do I know about isosceles triangles? What about the vertex angle in isosceles triangle? The vertex angle of an isosceles triangle, the angle bisector, right, goes through the midpoint of the base and is perpendicular to it. Okay, so here, right, maybe what some people are doing are introducing maybe a point X right here and drawing in the angle bisector and creating two overlapping triangles. They share AX, okay, they share Yeah, they just share AX, and that's a right angle right there. So yeah, I mean, I would buy that you could prove that triangle ABX is congruent to triangle ACB by HL. It's provable, right? Provable because you'd have to remember that the vertex angle of an isosceles triangle, the bisector intersects the base of the midpoint. The base is perpendicular to the base at its midpoint, right? That kind of theorem that came up earlier. Okay, so I'm not going to write that one out because that one's kind of a more advanced one to see, but I saw some people drawing that. I thought that was kind of cool. All right, check this one out here. Number 13, given premise. Here's our given premises. What do you do when you have given premises? You mark up the friggin' diagram. You do it. You mark it up. That's going to make your life hopefully a little easier in what you're going to kind of observe. Here, first of all, I think what now by this point in the problem, you should be realizing you should be looking for things that overlap. Okay, what are overlapping things potentially here? Well, we don't. Doesn't look like we have any angles that overlap any of these triangles. I don't see any angles that overlap that are shared. Like this one here, this triangle here shares angle A. You know, angle S, this is just this one triangle here, this other triangle here. They're obviously not congruent. Angle P is this triangle right here and this triangle right here. They're obviously not congruent. So that means our congruent side that we're going to work with is this, RQ. Okay, RQ is what we're going to work with. We're going to get to that later. So you could think about that now. You could think about that later, what's overlapping. I'll maybe think about that later in a second because, again, mark up the freaking diagram. Do it. Okay, so we have angle 2 congruent to angle 1, so we know those angles are congruent. We also know that angle 3 is congruent to angle 4. Okay, that's helpful, I think, right? Well, we're not talking about SRT and PTQ. We're not talking about that. We'd have to talk about this, right? We have a side here. We have an angle here, and we also have, this is a tricky one here. I'm going to erase this whole thing real quick so you can see the big thing here because the answer to this one's going to be ASA, right? It's going to be ASA. You might have trouble seeing it. So I'll try to erase this a bit here, but maybe remember what I just talked about a second ago. Remember how the problem's kind of set up. Because these triangles are congruent here by ASA. This one's not as many people are getting this one wrong as number 12, but it could be hard to see. So maybe I'll stick with gold here. Okay, because this larger angle is also going to be congruent to this larger angle here. That was the thing that was having trouble showing the diagram earlier. Why is angle SRQ congruent to angle PQR? Well, through the angle addition postulate, 1 plus 3 equals PQR, 2 plus 4 equals PQR. And what do we know about 2 and 4 and 1 and 3? They would sum to the same thing, right? 1 equals 2, right? These have the same measurement here. 3 and 4, these have the same measurement here. So PQR and SRQ, because part plus part equals whole, if you're adding equal parts to it, they would equal each other, okay? So this triangle right here, I'll do that in red, is going to be congruent to this triangle here in purple, PRQ. Okay, and the reason for that is this obtuse angle we know is congruent to that obtuse angle from what I just talked about, right? Two congruent angles added together is going to equal two congruent angles added together, the measurements here. So we have that angle, but we also have this. Angle 2 is congruent to angle 1. Right, so this acute angle of this purple triangle congruent to this angle here of this red triangle here. So we have an angle here, we have a large angle here, we have another large angle here, and we also have a side, right? A side, and that's included between the two congruent between the two congruent angles here. QR equals QR by reflexive, so we know it overlaps here. Okay, so what we got here is an ASA, and ASA correspondence, and those two triangles are congruent. Okay, so to wrap things up here, number 13, we got triangle SRQ is congruent to triangle PQR by reason of ASA. And that's that. Okay, that's the whole exit ticket wrap up here. So your answers should be within this. Please try to find them. Please try to revise today or tomorrow. Right, you can take tomorrow if you want to, but you do have to do it too. I will go back in and check out eventually if you did revise, because I want you to get it. Right, give yourself a chance to get it, and email me if you have any questions, because I want to give you that credit. You definitely have to revise your answers here. Thank you so much for watching. Hopefully it was helpful to you, but reach out if you need any more help. Take care, guys. Bye.